IQM. I just super briefly talk about myself so that you have an idea who's speaking now. So yeah, my name is Raphael Seidel. I'm from Germany, and yeah, I studied theoretical physics at RWTH in Aachen, and finished my master's degree in quantum field theory back in 2020. And yeah, after that, I started working at Fraunhofer Institute for Open Communication Systems in Berlin, where I decided that I'd like to pivot from quantum field theory towards quantum computation. I really liked the idea of doing something that is, on the one hand, very sciencey, but on the other hand, also has some actual real-world implications, which is not that much the case for quantum field theory. And yeah, back then, I started programming quantum computers via Qiskit, and I quickly realized that it is incredibly painful to do even the most simple things. And yeah, me and my colleagues, we then started to write abstractions and structure them and refactor them, and basically this cycle of things that you do when you're developing a software package, and eventually it turned into some form of language, and we decided to apply for some project funding, and we got it. And yeah, this turned into what is now Qrisp, a quantum programming language that operates on a higher level than just circuits. And yeah, Qrisp was open sourced and transferred to the Eclipse Foundation in 2023. And in 2025, IQM became aware, or I think they were already aware of it before, but they decided to offer me a role as the lead engineer for Qrisp, and to build up a team of Qrisp engineers working at IQM. So that made Qrisp effectively a multi-organization software package. And yeah, since then it has been growing. Many new people came into the ecosystem, and yeah, so a really exciting story, I would say. Okay, so enough about me. What is IQM? Yeah, IQM is really Europe's largest quantum computer manufacturer. And what makes IQM unique? What's really unique to us is that we focus on providing quantum computers that really sit at the customer's basement, so to say. We're not just providing access to our quantum computers in our basement, but we really deliver all the technology to the customer and make it run, and teach our customers also how to calibrate, how to essentially operate the whole system. And yeah, this can also be seen in this little slide here. IQM is really, when it comes to systems delivered, the largest manufacturer globally that has shipped the most quantum computers in the world. And IQM is also a really diverse employer. We have over 355 employees, 136 PhDs, a lot of funding, and also a lot of nationalities. So it's a really cool company. And yeah, if you ever get the chance to apply, I would definitely do that. And yeah, finally, a little overview over where IQM has delivered quantum computers. We have the United States, a lot of countries in Europe, and also in Asia. Okay, so much for IQM. Let me now switch slides and start talking about Qrisp. Okay, so what is Qrisp? So, or not what is Qrisp, let's start with the why. Why would we why would we even do this? And yeah, so for this, I have this slide that I like to show, which has this graph coming from some paper in the 2010, but it's showing the history of software development in the early stages of classical computing. And what we see here is that in the early 1950s, we had the majority of the costs being distributed towards hardware. But as the hardware matured, more and more cost was shifting towards software development, because this is there are so many things that come up if you're building software that this is really a major source of costs that if you want to build scalable computing systems. And yeah, so this it is reasonable to assume that something similar is also going to happen with quantum computing. My point here is that building better quantum programming infrastructure is not just some scientific endeavor, but there's really a commercial motivation behind this. There will be actual money being made out of having better programming systems simply because software development is less expensive. And yeah, there's also a more recent example of this phenomenon. So here we see a chart where you have GPUs compared against each other. AMD is in red and NVIDIA is in green. And this is not just performance, but is performance weighted with value. So the higher up, the better the performance for the money that you have to pay. And you see that the top of the chart is really populated by AMD. But regardless of that, NVIDIA is valued 10 times higher than AMD. And what is the reason for that? And yeah, many people in the computing industry will tell you immediately, it is CUDA. CUDA is their software platform, which really made it easy to program the GPUs, to also use them beyond just gaming applications. And they started programming, or they started creating CUDA 9 years earlier than AMD, and also poured in more money. And yes, a similar thing is most likely also going to happen in quantum. Okay, so let me start with ranting a bit about quantum circuits as a programming model. So yeah, my claim here is that quantum circuits as a programming model are really a dead end. And why is that? Because with quantum circuits, you cannot really do collaborative software development. And for that, two problems stand out: the signature problem and the modularization problem. And I will now get into what that actually means. Okay, so let's talk about the signature problem first. So if you're doing software development and you want to collaborate with your fellow software engineers, you need to be able to communicate what is your function doing, what input does it expect, what output does it return. But this is fundamentally challenging if you're operating on quantum circuits as a programming model. Because quantum circuits, they are just essentially like a list of qubits, and it's not really that easy to like distinguish what is an input, what is an output, where does one input even end, and that makes it really clunky to document how a quantum circuit acts as a function. And to illustrate that, I have this little code example here, which shows a subroutine taken from Qiskit that is just integer multiplication. And yeah, here we see the problem. So we call this integer multiplication circuit generation feature. And now it's really clunky to specify which qubits should be the input and which qubits should be the output. Because the qubits the input, this list here, needs to match specifically the requirements of this RGQFT multiplier. It's not really that clear which of these are inputs, which of these are outputs, because all is concatenated into a big list, and it's incredibly easy to make mistakes here. And yeah, in general, it's difficult to exchange. And this is just integer multiplication, which is arguably one of the simplest function that you could think about. And of course, this problem becomes even more problematic once you have more complicated functions. And yeah, we can take a look at the Qiskit documentation, how it is solved. And yeah, it's not really solved at all. They just specify how this RGQFT multiplier works. And then they give you some example of the circuit being generated. But this is not a good way to document your function signature. Okay, second problem that we have is the modularization problem. So what does modularization here mean in the first place? So modularization means that your interface has different submodules that you can exchange or develop in an isolated manner, so that you can optimize and reuse them at will. And modular software is really at the core of developing software collaboratively, because it allows us to have one person working on one module and another person on another module without them basically having to share the same brain, so that they can talk to each other via very clear interfaces where the developers agree this is how the interface looks like and this is how the modules exchange. So modular software is it's really important to enable collaborative software development. But yeah, once again, programming using quantum circuits as a programming model cannot be modular. And why is that? The reason is memory management. Why does memory management prevent the modular software development? The reason here is that different modules can require different amounts of ancilla qubits. And once you have you want to exchange a module, then you also completely need to rewire all your qubits to satisfy the new ancilla qubit requirements. Okay, and I gave a little example here with quantum adders. So adders are really neat demonstration of a possible quantum module because they represent a function that does essentially always the same. It adds two integers, but there are a lot of different implementation about adders. There are papers that document more than 200 different classes of adders, which is really insane. So adders are a really big field, and it's super nice to have this modularized with regard to other algorithms. And yeah, here we have two of the most popular adders. We have the Gidney adder and we have the Kucharo adder. The Gidney adder is really convenient because it is the best when it comes to T-count, but it requires, it requires linear amount of ancilla qubits, and the Kucharo adder, however, requires double the amount of T-gates, but it only requires a single ancilla qubits. Okay, so let's say now we have an algorithm that just says add two numbers. Okay, so then we want to modularize this. And if we're now using the quantum circuit module as our programming interface, then once we want to exchange the adder, we have to think about where are these additional ancilla qubits are coming from. From which module should they come? And once they have been used, where should they go again? Every time you exchange the adder, you have to essentially do this sort of mental exercise. And this is, of course, a highly non-modular thing, because every time you exchange the module, you also have to exchange the other modules. Okay, and yeah, here is where Qrisp is coming in. So Qrisp is a fully compilable high-level programming framework, which changes the point of view, so to say, away from the quantum circuits towards something that we call quantum variable. And so from what we know, it significantly enhances development aspects like prototyping, code size, maintainability, bug fixing, testing, etc., etc., etc. And yeah, it's also important to mention that, as I already mentioned initially, Qrisp is governed through the Eclipse Foundation. So it's not just one company, IQM or whoever, who is in full control of it. It's really a cross-organization project. And if you or your organization feel like contributing to Qrisp, then please let me know and we can make it happen. You can install Qrisp via pip install Qrisp. And there's a lot of documentation on qrisp.eu. And if you want to exchange with us, there's also a link to our Discord server, which is also very active and also very fun because people post a lot of memes. Okay, so to ensure that you believe me that this is not all just marketing talk, that I'm sitting here just talking about the benefits of software engineering, I'd like to highlight some of the things that we have been doing. One very cool and very recent thing is that we have the most efficient and also most scalable implementation of Shor's algorithm. We have a Python program that really produces the low-level representation of Shor's algorithm at 2,000 bits. Many of the other circuit engineering frameworks, they usually stop at around 20 or 30 bits because it's their architecture and their Python reliance make it incredibly non-scalable. We have the first end-to-end compilable implementation of the HHL algorithm. So there have been some circuit-based HHL implementations, but they did not involve the repeat until success component that is happening inside the HHL algorithm. So repeat until success means that there is a measurement, and based on this measurement, the algorithm performs another iteration or goes to the next part of the algorithm, which is the conclusion of the HHL algorithm.
Also,
yes. Sorry, what's that question?
for the purpose of this lecture, could you explain also the HHL algorithm in a few words for what it's used and how it's done? Yeah.
Yes. So the HHL algorithm is one of the earlier algorithms that provided exponential speed up for a task that is actually useful, and that task is solving linear systems of equations. So it is not some kind of drop-in replacement for your everyday linear solver, because there are a couple of restrictions. So for instance, the condition number of the matrix that you want to solve needs to be reasonably small. But people are actively working on finding situations where this exponential speed up can actually be harnessed. One thing that you should also know about the HHL algorithm is that it really contains a lot of rather involved subroutines. So one of the subroutines that it contains is Hamiltonian simulation. So the process of simulating a quantum system on the quantum computer, it contains quantum arithmetic, and it also contains this repeat until success component that I have been talking about earlier. It has been really challenging to make all of this work together. We did that. And another really cool feature is our block encoding module, which is really the latest release. This came out, I think, beginning of March or something. And yeah, block encodings are actually something that is extremely established in the quantum algorithms community, but so far there has not been really that much SDK support. Also based on the fact that many of the established SDKs, they don't really have these repeat until success features, which essentially provided all end-to-end compilation workflows here. Yeah, okay, so here's a little performance comparison of the shore performance. So there are some other frameworks here. We have Qrisp, Kibo framework, Qiskit, and some framework that I found on GitHub. And I mean, what you see here already is there are not that many shore algorithm implementations to begin with. So and yeah, it's usually they also always use the same paper. This is why the resource requirements look so similar for all of these. And this paper is like from 2003. So yes, this there are not that many shore algorithm implementations. And here's another comparison. This is a comparison between Qrisp 0.5 simulating different molecules and the Google equivalent open. What this comparison is counting is the RZ gate count. So now you might ask, why RZ gate? Because RZ gate is really the expensive thing when you're looking at fault-tolerant quantum computers. And yeah, for this type of simulation, you really need thousands, if not 10,000s of C0 gates. So this is not something that you can do on a NIST machine. So fault-tolerant is the name of the game here, and this is why we need to count RZ gates. Okay. Yes, let's get now to the framework overview. Yeah, I'm not gonna show you some kind of deep exponential advantage problem. My goal here is much rather to show you a bit how the programming in Qrisp actually looks like. And for that, we're gonna solve a very simple problem, and it is this equation here. And we're gonna do that by a Grover's algorithm. So for those of you who don't know what Grover's algorithm is, it's an algorithm that was initially invented to search databases with a quadratic speedup. But yeah, you can actually also do other things with it. So you're going to see how that works. Okay, so one crucial component of Grover's algorithm is the oracle. And the oracle is sort of the thing that describes what to search for. And so let's look at this. So first thing that you might notice if you are familiar with programming in a framework like Qiskit is that this oracle is not some kind of weird class, not some quantum circuit or whatever. It's just simply a Python function. And this is something that we make very sure in Qrisp that it stays this way. We want our programs to be actually like programs compatible with Python infrastructure. So our usually our code looks like this. Okay, so this oracle receives a quantum float, and this quantum float is then multiplied with itself, which returns yet another quantum float. And then this returned quantum float is compared with the classical value 0.25. And this whole thing now returns something that's called a quantum bool. And then we apply a Z-gate, which is required by Grover's algorithm because you need to do this phase flip. And yeah, this almost concludes the oracle. The one thing that we need to do is essentially disentangle all the temporary variables. And this is why we have this auto uncompute decorator. So what the auto uncompute decorator does is it's analyzing the function and figuring out which temporary quantum values are appearing in this function, sort of the local values. And once these are identified, it then performs an algorithm that uncomputes them. So it disentangles them. Okay, so how does that look like in a circuit? Yeah, let's just go through this program step by step. First step that we have is the multiplication, or much rather the squaring. And this can be seen as this big block here. Yeah, the details of the multiplication algorithm, they're more relevant. So this is why it's drawn like as a big box. So next we have the condition evaluation that the result is actually equal to 0.25. So this is this multi-controlled X gate here. Then we have the phase tag, which is this gate here. And finally, we have the uncomputation, which is reversing all the stuff that happened before. Okay, so how does this look like when embedded into Grover's algorithm? So to perform Grover's algorithm, we first allocate a quantum variable that is done here, and we give it 3 mantissa qubits, the exponent -1. -1 means that the search space will have a precision of 2 to the power of -1, so 0.5. So it means that the search space can represent numbers like 0, 0.5, 1, 1.5, etc. And we want the whole thing to be signed. Okay, then we bring it into uniform superposition. We determine the amount of iterations according to the literature, and then we just perform a loop, which is oracle and diffuser in alternation. And yeah, this is the circuit. It essentially describes what we already saw in the code. We have the quantum float, which is initialized through H gates. Then we have the oracle being executed and the diffuser, and then we repeat the whole thing. And yeah, this is Grover's algorithm. And once we throw this into a simulator, we see this picture. So we see that there are 2 peaks here, one at 0.5 and one at -0.5. And yeah, if we go back to the question that we were asking, what is the solution to this equation? Then yeah, we see, okay, this was in fact the solution of this equation. Yeah, so before I go to the next section, I'd like to stop and check if there are any questions that came up.
Yeah, feel free to ask any questions right now. Maybe the microphone. Yeah. Go on.
Can you give a little more details about these gates you mentioned, the H gate, the Z gate? What's the idea? Because there's look like sort of a standard operations, but to do this like us, it sounds like magic.
Sorry, could you repeat? It's difficult for me to understand.
Can you give some overview of what these gates do? The H gate, the Z gate, what's the some kind of standard operations for that?
Yes. Okay. Yeah. So the H gates and some of the quantum gates, they're purely classical, right? For instance, an X gate corresponds to a NOT operation. An H gate is you can consider this as a gate which brings the qubit into uniform superposition. So it applies. If you plug a 0 qubit in, then you have a superposition of 0 and 1. And a Z gate flips the phase of the the zero. It flips the face of the 1 state, and it doesn't flip the face of the 0 gate state. If that helps.
Yeah, it does help, but I guess there's some standard set of these gates. Can you give us a few more details about these? I assume it's not just the H and Z gates.
Yeah, so they are documented in a lot of places. So I guess if you just type it into your favorite AI agent and make them explain what is an H gate, then it's probably like gonna tell you how that works.
Okay, thank you.
How is this simulated in Python? Because it's not, you don't have real qubits.
Yes. So the whole thing can be compiled to a format that is called OpenQASM, and OpenQASM is sort of the lingua franca among NISQ circuits. And so once we have it in OpenQASM, we can actually like run it on a lot of simulators. So for instance, the Qiskit simulator, but we also have our own simulator in Qrisp, which is making use of sparse matrices. So matrices where there are a lot of zeros, it simply doesn't represent these values as zeros, but only tracks the values that are non-zero. And yeah, but essentially it is contracting unitary matrices in Python, yes. Does that answer the question?
Yep, thank you.
Maybe I can just address the first question real quick, just so that it makes sense. So like in classical computation, you have, like you can prove that you can do any computation with just ends and ors, right? This is sort of like the analogy here, like these are these sets of Toffoli gates, which like you can provably do any computation with just X, Z gate, and something that connects to gates, which is like a control gate, which I guess there is no example on this previous slide, or maybe there was on one of the previous, but when you see like a line that goes across the circuit, it is like a control gate, which is like your multi-qubit gate, and you can basically probably do any computation that you want. Yeah, like this. This is a control X gate. So if the first qubit is 1, it does like a bit flip on the second one, and if it's 0, it does nothing.
So any more questions right now, or we should continue?
If there are more questions, I'm happy to answer them. But okay, so the section of the room that I can see doesn't seem to have any questions.
Yeah,
so
we may continue, yeah.
Okay, perfect. Okay, then yeah, let me go to a topic that maybe goes a bit more in depth. Yeah, probably also have to skip some parts because already running a bit behind schedule. Okay, so yeah, as I mentioned to you that memory management is something that is extremely important when it comes to modularizing the software development, and to get the full leverage out of that, I'm going to talk a bit so that you can understand a bit better what's going on. Okay, so in a Qrisp memory management lifecycle, there are two components. There's the allocation and there's the deallocation. So in order to allocate qubits, you can simply call the quantum variable constructor, and it will give you the amount of qubits that you requested. So for instance, for the quantum float, which is a subtype of a quantum variable, it indeed allocates 10 qubits. So if you call the quantum bool constructor. It's you don't have to specify any number because the bool is always just 1 qubit. Okay, so allocation happens through the constructor. Deallocation can be done in 2 different ways. So the first thing that you can do is manual uncomputation. So after you allocate, so you do something, an algorithm or whatever, and then you want to, if you want to deallocate them, you have to manually uncompute. You have to bring the quantum variables back into state 0. Why is this the case? I'm going to talk about this soon. For now, we just accept that you have to bring it back to 0 before you delete it. And then you can, once you have brought it back to 0 manually by just reversing what you have done before, you can just call the delete method, and this way you tell the compiler you can free this up. You can also automate this, and we also saw this in the Grover example by calling either this .uncompute method, or you can also use this decorator that uncomputed all the values. Okay, so how do we now get the memory management out of this? So the goal of the memory management is to reduce the amount of qubits, which are the quantum memory, so to say, of the overall program. And for this, we have this compile method. So to this compile method will, when we call it on the QS attribute of the quantum variable, will give us a quantum circuit. And for this, we can count the amount of qubits that is showing up in this quantum circuit. And so an important thing here is that the call order of the allocation does not matter. So it is transforming this internally into a graph representation, and once this graph representation is reached, the call order is essentially lost, and therefore it's not important in which order you allocate it, A, B, and S. It will find a really good strategy to perform the memory management. Okay, so let's skip this. Okay, so uncomputation is something that I just mentioned, is something that is important to reuse qubit resources that are no longer required. And the classical equivalent here is really garbage collection. So essentially, you can free up memory that is no longer needed. But it goes beyond that. This is not just a resource question. Some algorithms even require uncomputation. So, for instance, Grover's algorithm, as we just saw, requires the data register to be disentangled, and this can only be reached through uncomputation. So how can we get to the 0 state? So there's this really naive strategy which says, you can just measure the qubit, and if you happen to measure a 1 state, then you perform a bit flip, and if you already get the 0 state, then you're fine. This is not really suitable, because the measurement will collapse the superposition of all the entangled qubits. And so this is a sort of a global side effect, which essentially destroys the inner workings of your quantum algorithm. We don't want that. And it is precisely this phenomenon that's also at the core of the EPR paradox. If you introduce Einstein thought experiments, then I recommend you to look this up. Okay, and uncomputation is, as I already explained on one of the previous slides, the strategy of reversing all the steps that were necessary to compute what had to be done to compute qubit Q, and then we end up in the 0 state. But the problem here is that it can also be a bit ambiguous to identify which steps have actually been necessary to perform the forward computation when you want to perform the backward computation. So for instance, here, which parts of these circuits really contributed to the computation? So yeah, obviously the multiplication for the comparison is also relatively clear, but is the Z gate something that contributed to the computation? Maybe, but we also don't want it to be reversed, but because Grover's algorithm requires this Z tag, so it is it's ambiguous. Yeah, the point here is that doing this uncomputation manually can be something that is super cumbersome, and we want that automated. Okay, so let me skip that. Yeah, yeah, to reach this automation, we have this algorithm called uncomp, which was devised by researchers from ETH Zurich. And what it gives us is a way to yeah, find uncomputation strategies for a relatively wide class of circuits. And yeah, we have a generalized version of this implemented in Qrisp, and it allows us and our users to not have to deal with uncomputation at all, which is also very helpful. Okay, so yeah, I mean, I already talked about the uncompute method and the auto uncompute decorator. You already saw that in the Oracle. Okay. Yeah, let me skip that. Yeah, okay, so let's go to quantum environments. So what is a quantum environment? So a quantum environment is a particular section in your code that undergoes a user-specified compilation procedure. So it could be essentially interpreted as higher order quantum function. And yeah, one example is this control environment. So what the control environment does is it performs this incrementation here if B is in the 1 state. So you could see it as some kind of if state. The one crucial difference to the if state is that a classical processor would only execute if this is actually true. But for a quantum computer, we don't know if this is true because it can be in superposition. So it has to execute it regardless. So yeah, it's a bit different from an if statement, but it also has its similarities. And yeah, an important thing is that users also can create their own quantum environments. Okay, so now let me talk about the most important environments. So the one that you already saw is the control environment. Yeah, and it allows us to have subroutines in controlled manner. And an important performance feature is that if you're nesting control environments, then it's not just putting controls on everything, which would be very expensive, but instead it is coming up with some strategy that is sort of recursively computing control values such that the body of the innermost environment only has to be controlled once. And yeah, this is a really neat showcase of an important class of program optimization, which is only possible due to high-level algorithm structure. And yeah, so this is also something where Qrisp really shines compared to circuit-level frameworks, because in circuit-level frameworks, you usually code up some quantum circuit, and then you throw some general purpose optimizer onto this quantum circuit and hope that it finds some symmetries or structure in the circuit, and then it returns you another quantum circuit, which is then optimized. But here we can really perform optimizations based on the structure of the high-level input code, which is something really cool, I think. Okay, and so this slide demonstrates what I just mentioned with the nested control environments. So here we have two control environments. So first one is controlled on this quantum variable B. The second one is controlled on this quantum variable C. They have 3 and 2 qubits respectively, and the innermost is executing a Z gate. Okay, so now let's go through the circuit to understand what's happening. So first step is entering the control environment that is controlled on B, which is this gate here. Okay, so then it is executing the X gate on A. This is controlled on the control environment 0 value, the X gate, and now the second control environment is executed. But the computation of this second value is not just naively controlled on the values of B, but it's simply taking the control value of the first control environment and based on that computing the control value of this innermost control environment. So then it is executing the Z gate, and finally it is reversing all the steps for the computation of the control values such that they can be garbage collected. Okay, another important environment is the inversion environment, which is relatively straightforward to understand. It is simply daggering all the quantum parts that happen inside it. So daggering simply means executing everything in reverse. And final environment that I want to talk about is the conjugation environment. So the conjugation environment performs this sort of mathematical structure where we have this sort of sandwiching between two operators called V. And so the conjugation environment allows you to code up adders, quantum Fourier-based adders, really quickly. So this is an example of a Fourier adder where you have just this conjugation with the quantum Fourier transform, and inside you have this loop over phase gates, and this gives you the adder already. And here there's another optimization that is only possible due to high-level code structure. And the reason for that is that if you want to control a conjugation, you can also just control the inner part. Because if the control is not triggered and this mark value is not executed, then the V gates, they just cancel each other out. So we end up with overall the identity. Okay, and here we have again a similar program as we had earlier. So inside we have the adder that I just discussed in the previous slide, but this time it's called inside a control environment, which is again controlled on some 2-qubit variable B. And inside here we have these control values. And you see that the QFTs themselves, they're not controlled on the values here, precisely because of this identity here. Okay, so this is the last section of the talk. So maybe we again have some time for questions.
About the most simple example, the first one. This one. We are reversing the operations, but where are we uncomputing in the code? Shouldn't it be explicit or with a decorator stated?
Yes. So the control environments themselves take care of the management of these control values. So as you might see, these control values, they don't show up in the high-level code in the first place. So the user doesn't really have to think about this. It's just that internally, once the control environment is entered, this this control value is allocated, and once the control value is exited, it is also again uncomputed.
Okay, and what's actually the point of this code block?
The point is to demonstrate that the nesting behavior of the control environments is it is not super naive. So a super naive implementation would probably just have this. Wait, no, it's now hard for me to draw, but this this multi-controlled gate here also just controlled on B0, B1, and B2 because they all live in this control environment B. Okay, and having these very large controlled X gates can be very expensive in terms of gate counts. So it's important that you properly decompose this. And the control environment allows you to have this decomposition strategy.
Okay, thank you.
Do you have more questions?
I am not sure if I understand correctly the compute in the reverse part, because when we measure, we change the state, but doesn't it happen like randomly? So how do we know? Actually, yeah, it's like 0 or 1, but also the phase. I don't know how exactly works that when we measure or see the qubit, it changes the state or the phase, so that we can reverse or uncompute it. Or
so I'm not exactly sure if I completely understood the question, but I will try to answer it, and then you can tell me if it was the answer. So you're correct. We don't know exactly in which state it is in 0 or 1, but we know how we got there. So if we just reverse this getting there, then regardless of whether it was in the 1 or in the 0 state, we're going to end up in the 0 state again, because we know that we started in the 0 state. Does that make sense? Or
okay.
did it even answer the question?
Yeah, it answered it because we know the starting point, so we start from 0. That makes it a little bit clearer. But yeah.
Yes.
The question was maybe if we don't know the starting state, but yeah, that's the idea that we do know. Then
Yes.
okay, thanks.
Yeah. Maybe also seen here in this circuit. So in this circuit diagrams, we always assume that we start in the 0 state, and so the computation performs this multi-control X gate. Then we have the Z gate, and so in this area of the circuit here, this qubit is indeed in superposition. It can be anything, 0, 1, anything in between, and we indeed don't know it. But since the values that were relevant for computation are still available, we can simply reverse this, and all the states that were 1 are going to get flipped, and all the states that were 0 are not going to get flipped because they have not been flipped in the first place. And this way we end up in the 0 state again, and then we can deallocate again.
I have a very quick follow-up question, because it was actually a really good question. What if you have partial measurements that do change other parts of your quantum circuit? Do you even allow partial measurements in your language? Because then you cannot reverse it.
Yes. So that's actually a question that goes extremely deep. So we, in order to enable the framework to have mid-circuit measurements, which also allow us to do real-time computations. So computations that are based on the measurement results and need to conclude within like nanoseconds. For the quantum computation to continue, we essentially revamped the whole compilation pipeline. And as it turns out, in this new compilation pipeline, the intermediate representation that represents the program does no longer allow the uncomputation algorithm. Because the uncomputation algorithm makes some assumptions about the structure of the program, which are no longer met. That's a bit unfortunate, and we're still figuring out how to solve that. But in this old compilation pipeline, where there are no meaningful mid-circuit measurements, the uncomputation still works. I hope this answers the question. It goes incredibly deep, and I could talk a lot about this, but yeah, so if you want, you can write me on Discord and then I give you more details.
We have another question.
Yeah?
Mine is a simplified version of his question. So basically, I get how we reverse this qubit, but how does this not impact the other qubits that were entangled with it? Because
sorry, it's really difficult for me to understand, but maybe you holding the mic wrong, I don't know, but it's difficult to understand.
how does it not impact the other qubits that were entangled with the one we're reversing or uncomputing?
Ah, okay, yeah. This is also so this is goes back to the implementation of this algorithm that I was mentioning, uncomp. Where is it? Wait. Yes. Okay. So this algorithm here proposes a structure of a circuit, or a representation of a circuit that's called a special version of a directed acyclic graph. And in this directed acyclic graph, the uncomputation means that you're essentially inserting nodes into this graph at certain positions. And the way that the nodes are inserted are specifically engineered to make sure that the other qubits are not affected. So again, you can see it in this circuit here again. So when we're uncomputing, damn it. When we're uncomputing this qubit here, then the only thing that is operating on the other qubits are these multi-controlled X gates. So since these are just controls, they are not like really operating in a sense of changing on the control values. So they touch the control values, but they leave them where they are, if that makes sense.
Thank you.
Are there any more questions? So we could continue.
Perfect. Okay, then let me go to the final section. Final section is about the operators module. Okay, so with the operators module, we enable our users to describe, optimize, and simulate quantum Hamiltonians. And what can we do? We can have the qubit operator, which is a way to represent Pauli strings, but also other operators. And we also have the fermionic operator, which allows us to describe ladder operators, which are very heavily used in quantum chemistry. Maybe at some point we are also going to have a bosonic operator, but this is still not yet done. And yeah, there are a couple of applications of the operators module. So one, and probably the most well-known one, at least in this computing, is VQE. Then you can also do Hamiltonian simulation, quantum chemistry, and also optimization problems. Okay, let me get a bit more into that. How does that work? So to create an operator, you simply import these capitalized letters from the Qrisp.operators module, and then you can set up Hamiltonians. So this is some Heisenberg Hamiltonian, and you can also have some scalar coefficients here. And here you also have these annihilation and creation operators that are called A and C. And here you see the mathematical version of these operators. So the X, Y, and Z, they're just the Pauli matrices, but now written in cats and bras. And so what might be maybe a bit less well known are these annihilation and creation operators. So this is the annihilation operator. If you operate with it on a 1 state, then it gives you a 0 state. And if you operate with it on a 0 state, then it just gives you like an actual 0, not a 0 state, but just a 0. Yeah, and yeah, as you can see in this example, it supports matrix arithmetic, so multiplication, addition, scalar multiplication, and also daggering. And it also contains several functions that simplify and optimize these operator representations, because if you're starting to build an algorithm out of this, then usually if you have a more simple operator, then the algorithm also requires less gates. Okay, so what I just talked about was the qubit operator, and now let's talk about the fermionic operator. So for the fermionic operator, we have just two. We have the fermionic ladder operators, and they are denoted through this non-capital A and C. And so maybe I should also say a few words about what this is actually about. So if you're describing chemistry, in particular atoms and molecules, then you have these orbitals where the electrons can live. And it turns out that the way to describe these orbitals is through these fermionic annihilation and creation operators, and a crucial property that they have, that they are anti-commuting. So if you are exchanging the order here, so if you would have C1 times A2, then this would be equivalent to A2 times C1. So this is the anti-commutation relation. And yeah, we also have functions that simplify the fermionic operators using these anti-commutation relations. And another really cool feature is that you can essentially load molecules from PySCF. PySCF is a quantum chemistry library that is really quantum chemistry. So it's not about quantum computation itself. It's really about chemistry done in the quantum realm, so to say. And yeah, they provide some infrastructure to describe molecules. And what we see here is the H2 molecule, and it's these numbers here, these 0, 0, 0 are really the spatial coordinates. So this is an H atom sitting at the origin, and this is another H atom sitting at the origin plus 0.74 angstrom in the Z direction. And yeah, so using PySCF, you can load this molecule data structure, and then with the Qrisp fermionic operator, you can import this data, and now you have the Qrisp Hamiltonian. And yeah, can do stuff with it. And yeah, I should also mention that it is possible to transform from the fermionic operator to the qubit operator, not the other way around. And in many cases, you don't want to do that. Keeping it in the fermionic operator form is more efficient than the qubit operator, but it is possible. Okay, so what can you do with the operators? So one of the most important applications is Hamiltonian simulation. So that means that you're plugging in the operator, and then you are performing on the quantum computer what would happen in nature. So you're loading the molecule data from the quantum operator, and then once it is in Qrisp, we can generate the quantum circuit that is simulating how the molecule would behave in nature. And yeah, to do that, we just create some example operator, and then we call this trotterization method, which gives us a function that actually performs this simulation. And yeah, to perform the simulation, we initialize a quantum variable in the state 1, 0, 0, 0. And now we can call this function u with yeah, with the time value. So in this case, it would simulate the operator O for 42 atomic units of time, and trotterization steps 1. And yeah, so there are a lot of optimization layers below that. One of them is automatic term grouping. And another really cool feature is symbolic parameter support, which means that we don't have to specify an actual concrete number like 42 here, but we can also just plug in a SymPy value, and then we have a parameterized circuit that describes the time evolution with a parameter. Okay, and second most important application of the operators module is computing expectation values. So as a reminder, this is how we compute an expectation value of an operator in just textbook quantum mechanics. And yeah, how do we do this in Qrisp? So in Qrisp, we do this by specifying some state preparation routine that essentially tells the compiler, how can I create this state? So as you know, it's not possible to copy states in quantum mechanics. This is why we need to give the compiler the state preparation function. And yeah, so what we're going to do now is we create this Hamiltonian, and then we can call this method expectation value with the state prep. And this once again gives us another function similar how we had it in the trotterization case. And then we can evaluate it with the value theta equal to pi over 2. And yeah, all of this is highly probabilistic. So we can also tune the precision. And by dialing up the precision, it essentially means that our quantum computer is performing more shots. So yeah, if you have an infinite shot budget, then you can compute these expectation values infinitely precise. And yeah, if you, like us mere mortals, only have a fixed budget, then you have to live with some error. And yeah, for operators that are somehow small, I don't know, only operating on like maybe 15 qubits or something, you can also compute the ground state energy of the operator purely classically by yeah, constructing the matrix and then throwing some NumPy algorithm at it, which is going to compute the ground state energy. Okay, yes, so before we have the next round of questions, let me briefly summarize. yeah, so in order to make quantum computing a reality, we need to make it as accessible as possible. Within Qrisp, we have many repetitive programming tasks that can be automated. And with Qrisp, we can have very efficient algorithms, very quickly formulated, which allows us to very quickly iterate over a lot of ideas. And we can have high-level algorithm research. Yeah, we have okay, this is from an old slide, so yeah, we don't have that anymore. Yeah, we have a state-of-the-art quantum compilation routines. Okay, so yeah, this concludes the first part of the talk. Please install pip install Qrisp.
This is the environment, and now do you have any questions additional? Okay, just some preparations we've sent to you through the emails that you've applied for this event. The links for Google Colab, which essentially is a platform where we have set up the environment. You just run some cells, and based on that, you have you can implement and code. And, let me know if you have any problems. We'll fix them. But there should be placed a pip install for Qrisp. It is right now commented, so uncommented, run the block, and then we can continue.
We will need some 2 minutes, for example, so people could prepare.
Mm-hmm.
Yeah, and we have also one question.
Yes.
Hi, thanks again for the quick lecture. I'm just trying to build a mental model of where Qrisp sits compared to other languages. Would you say that Qrisp is trying to be more declarative, i.e. to define modularization that do some basic stuff like you mentioned others? Because if you're trying to be declarative, I don't see very many like category theory stuff, and I just see Qrisp is building on top of like circuit description primitives. But on the other hand, you mentioned stuff like creation and annihilation, which then again are category theory concepts. I guess my question simply put is, where would you put Qrisp on that spectrum? Is it closer to Qiskit, or is it closer to stuff like Q# and ZX calculus?
Okay, so first of all, the creation and annihilation operators, they're not the ones that you might know from category theory. They are really the just names for these matrices. They are not something that is inherently deep. I mean, for the fermionic operators, it might be a bit more complicated what these operators actually represent, but it is not rooted in category theory. Yeah, so, but where does it sit? Yeah, so I would say that it is very comparable to Q#, but I would say the one distinguishing difference is that, at least in my feeling, Q# is more of a demonstration of how a language could look like, because it is not really catering towards the requirements of everyday data scientists, which begins with the requirement of having it in Python, because you need the Python ecosystem to actually do scientific stuff. If you need, for instance, a ZAT solver to do your compilation in Q#, then you need to write the ZAT solver yourself. You cannot really rely on this kind of stuff being available. And yeah, for this reason, I think the general position in the stack is similar to Q#, but the motivation on why we're doing this is much less about just demonstrating how it could look like, and much more about actually building something that works for building large-scale algorithms.
Okay, so you're trying to be like more declarative, I guess, like higher concepts.
Yes, you could say that, but at the same time, because we also have it's going to become a bit more clear in the upcoming notebook, we also support writing programs 100% in terms of gates. It's just that once you have a function that performs your desired function in terms of gates, then you can work on top of that. You can abstract that. So it's not 100% declarative, but it's essentially providing the infrastructure for low-level people to write their low-level code and high-level people to write their declarative stuff.
I see. Okay, thank you so much.
You're welcome. Thank you for the question. Okay. So maybe people are still setting up. So unfortunately, the talk went way longer than I originally planned. So we have to hurry a bit here, and most likely we're also not going to finish it. If you're interested in finishing this by yourself, I think a lot of it is very self-explanatory, and I can just give you the rough overview over what we're doing here. Okay, so what is this notebook about? It's about one of the most famous quantum experiments. It is the double slit experiment, and the idea here is that we have some source of a particle, so for instance an electron or a photon or whatever, and it goes through this double slit structure, and then on the other end there's a screen, and on this screen we see this interference pattern. And the interference pattern is really the fundamental proof that the electron actually went through both slits, because the interference pattern can only be explained through a wave. It's actually the very same interference pattern that we see when we would actually have sent a wave through the double slit. Okay, and we now want to perform this experiment on the quantum computer, and for this we're going to follow a three-step schedule. So the first thing that we're going to do is we prepare the slit state. The slit state means essentially the state that the electron is in the very moment it passes through the slit. And that means that the quantum state has all zero amplitudes unless it is actually inside a slit. Okay? This is the slit state. Second step is we are steering the beam. This means that we can sort of redirect in which direction this electron beam gun is pointing, so to say. Finally, we're going to do the propagation step. So from the double slit to the screen to perform or to transform the slit state into what is happening on the screen. Okay, and here is some picture of a physical experiment to show you that I'm not lying to you, that this is a thing. And here's another picture. Okay. Yes. First thing is to perform some imports. I already did this. In your case, it might take some time.
Could you just zoom a bit at the preview?
Yes. Okay. In your case, it might take some time because there's a lot of things to import here. Qrisp is really relying on a lot of scientific computing infrastructure, so the import can take a few seconds. Okay, so yeah, let's get to the encoding of the slit state. So what we're doing here is we're gonna set up a quantum float, and the quantum float is gonna represent little chunks of the slit. And so the encoding works essentially like we see in the picture here. So we say that the particle is in one of the slits. It was between 13 and 17 and 19 and 23. So another way to phrase this would be that these numbers here, they represent centimeters, and the slits, they're actually positioned between 13 and 17 and centimeters and 19 and 23 centimeters. Okay, so that should be easy to understand. Okay, so now let's get to the actual coding part. Yeah, then let's execute this cell. And yeah, so first we're creating a quantum float that represents the numbers from 0 to 31. And yeah, we just calling print on the quantum float, which triggers the simulation. And we see, so it's initialized in the 0 state. And yeah, we can also perform some initialization ourselves. We can initialize into the 14 state. And we see this here. Okay. And we can also call the H gate on all of the involved qubits, which brings it into uniform superposition. So now we have a superposition of all the possible positions. So from 0 to 31. Okay. Yeah, so next step is now to prepare the slit state. And yeah, for this, we're going to use Grover's algorithm. And again, I have to be really fast here because there's not that much time. So yeah, the idea is that we initialize the slit state by using Grover's algorithm to search for the positions that are inside the slit. And for that, we're going to create an oracle that tags the states that are inside the slit, and then we're going to use the diffuser to amplify that. Okay, and yeah, this is the oracle needs to answer the question, is this position inside the slits? Okay, and for that, we're going to use some quantum arithmetic. In particular, we're using arithmetic comparisons to figure out is this actually inside the slits or not. And to figure out if it is inside the slits, we say, yeah, it is larger than the lower bound or less than the upper bound. Okay, and yeah, here's a little code example that demonstrates you how these quantum comparison work. So here you have a quantum float, which is initialized into the state 14, and two classical values, 13 and 16. And you can just use the comparison operator to perform the comparison. And this gives us, again, another quantum value. And yeah, and this quantum value is now of type Boolean. And we see this here. So above lower is indeed true, because yeah, we initialize into 14, and it's now it's indeed larger than 13. Okay, so now comes the first exercise, and yeah, as I mentioned, unfortunately not enough time to go through the exercise in detail, but I am just going to give you the rough overview of what you have to do here. So this is a function which receives a quantum float and a tuple of two classical values called slit, and it is supposed to return a quantum bool type that is true only if the quantum float is inside the slit. And yeah, for that you have to use the MCX gate to compute the AND value, and yeah, I will not be able to do that. So yeah, I hope it's fine if I maybe overextend for 5 minutes. Otherwise, I would wrap it up now. Is that okay? Or
Yeah.
all right, perfect.
We have one question.
Yes.
No problem. Sorry.